Covalent bonding. When nonmetals react with each other, they attain noble gas configuration by sharing their valence electrons between themselves and completing their valency. This type of chemical bonding is called covalent bonding. Two or more than two atoms join together to form a molecule, and they have a covalent bond between them. Dot and cross diagram is used to represent the covalent bonding amongst the atoms in a molecule. These atoms can be identical or non-identical as well. H2. Hydrogen has one electron in its shell and needs one more to attain duplet configuration. It shares its valence electron with another hydrogen atom to achieve its duplet configuration. HH single covalent bond is formed in the hydrogen molecule. Cl2. Chlorine is in group 7 of the periodic table, which means it has 7 valence electrons in its valence shell and needs one more to attain octet, 8, configuration. It shares its valence electron with another chlorine atom to achieve its octet configuration. Cl single covalent bond is formed in chlorine molecule. O2O equals O. Oxygen is in group 6 of the periodic table, which means it has 6 valence electrons in its valence shell and needs 2 more to attain octet, 8, configuration. It shares its valence electron with another oxygen atom to achieve its octet configuration. O equals O. Double covalent bonds are formed in oxygen molecule. HCl. Hydrogen has one electron in its shell and needs one more to attain duplet configuration. It shares its valence electron with a chlorine atom to achieve its noble gas configuration. HCl single covalent bond is formed in hydrogen chloride molecule. N2. Nitrogen has 5 valencies and needs 3 more to attain duplet configuration. It shares its 3 electrons in its valence with another nitrogen atom to achieve its octet configuration. A triple covalent bond is formed in a nitrogen molecule. H2O. Oxygen has 6 valency, needs 2 more electrons to attain octet configuration. It shares its 2 valence electrons. 2 pairs of valence electrons form 2 lone pairs, with 2 hydrogen atoms to achieve its octet configuration. Single covalent bonds are formed between hydrogen and oxygen atom, and a water molecule is formed. CH4 carbon has 4 electrons in its valence shell and needs 4 more to attain octet configuration. It shares its valence electron with 4 hydrogen atom to achieve its octet configuration. CH single covalent bond is formed in the methane molecule. C2H4 carbon has 4 electrons in its valence shell and needs 4 more to attain octet configuration. When 2 carbon atoms form a covalent bond, they share 2 pairs of electrons that are C equals C. The remaining 2 electrons of carbon in its valence shell are shared by 2 hydrogen atoms to form a single carbon-hydrogen bond. Note, when 2 electrons are shared, a single bond is formed, represented using a single line in the structural formula of the compound/molecule. When 4 electrons or 2 pairs of electrons are shared, a double bond is formed, represented using a double line in the structural formula of the compound/molecule. When 6 electrons or 3 pairs of electrons are shared, the triple bond is formed, represented using 3 lines in the structural formula of the compound/molecule. Allotropes are the same elements with different structures called allotropes. For instance, O2 and O3 are allotropes. CO and CO2, both are not allotropes. Covalent compounds can be simple or giant covalent structures. Both have varying properties because of their structure and bonding. Simple molecular substances, iodine molecules, are formed by 2 iodine atoms sharing a covalent bond. However, intermolecular forces exist between iodine molecules. That is why the little amount of heat can break the weak intermolecular forces, van der Waals forces. This implies that simple molecular structures are highly volatile and are usually liquids or gases at room temperature and pressure. Those with larger molecules are solids at RTP. They have low melting and boiling points. They are unsolvable in water and solvable in organic solvents. These substances cannot conduct electricity due to unavailable free-moving electrons to carry charges. Exceptions include graphite. Giant molecules, graphite, diamond, and silicon dioxide are all giant molecules because they have lots of atoms held together in strong covalent bonds to form giant molecular structures. Their properties are also different. Silicon dioxide. It is a 3D tetrahedral structure. C has 4 valencies and shares its single covalent bonds with 4 oxygen atoms to form a giant SiO2 compound. It can only melt at high temperatures. Graphite diamond. Each carbon is directly attached to 3 more carbon atoms. Each carbon is directly attached to 4 more carbon atoms. It conducts electricity because of free-moving electrons. It does not conduct electricity. It consists of layers, and layers can slide. That is why graphite is soft and used as a lubricant. It is hard because of its 3-dimensional structure. Graphite is 2-dimensional. Diamond is 3-dimensional. The formula of both is the same, C. The formula of both is the same, C. Properties of giant molecular structures. All giant molecular structures have high melting points because a large amount of energy is required to break the network of strong covalent bonds. All simple molecular structures H2, CO2, etc. have low melting and boiling points because a small amount of energy is required to break the weak intermolecular forces. Diamond has a higher melting point than graphite because a greater number of bonds have to be broken in diamonds. Diamond is hard because of strong covalent bonds amongst carbon atoms in its giant structure. When an equal amount of graphite and diamond are wholly burned, they produce the same amount of carbon dioxide as the only product. Diamond cannot conduct electricity because of unavailable free-moving electrons, whereas graphite can conduct electricity. In graphite, each ring consists of 6 carbon atoms. Uses of graphite. 1. It is used as a lubricant because of its sliding layers. 2. It is soft and smooth. It is used to bake along with clay to form pencil lead. In between the layers van der Waals forces are present. 3. It is used in inert electrodes because of free-moving electrons. Uses of diamonds. 1. It is used in jewelry because it is shiny. 2. It is used in glass cutting and drilling because diamond is hard. Physical properties of covalent compounds. They are solids, liquids, and gases at room temperature and pressure. For instance, silicon dioxide, water, and carbon dioxide gas, respectively. They have lower melting and boiling points except for giant molecular structures such as silicon, SiO2, graphite, and diamond. They do not conduct electricity except graphite and an aqueous solution of acids. An aqueous solution of acids conducts electricity because bonding changes from covalent to ionic when molecules dissociate in water to form ions.